Have you ever wondered how a robot actually knows where it is or what it's doing? It seems simple, but it's one of the trickiest problems in all of tech. Today, we're cracking the code on this thing called state estimation. It's the secret sauce that makes everything from robot vacuums to self-driving cars actually work.
So let's just dive right in. Why can't we just tell a robot, hey, move forward 1 meter, and have it just do that perfectly? Why is a command that sounds so basic, in reality, so unbelievably difficult for a machine to pull off?
Well, it all comes down to the messy, unpredictable real world. See, there's this huge gap between the perfect plan we have in our heads and what actually happens. You tell it to go 1 meter, but its wheels slip a little, the floor isn't perfectly flat, the motors aren't flawless. You expect it to measure a wall 3 meters away, but its sensors are, well, they're noisy. They give slightly different readings every single time. It's a world of approximation. And this all boils down to two main villains: uncertainty in a robot's own actions and noise in its sensors.
Okay, so if the world is so messy, how on earth do we deal with it? You might think the answer is to build more precise, more perfect robots, but that's a dead end. The real breakthrough was a total shift in mindset. Instead of fighting uncertainty, we have to embrace it. We have to start thinking in probabilities.
And that brings us to the absolute heart of this whole thing, a concept called belief. See, a smart robot doesn't try to know its one true location. That's impossible. Instead, it keeps track of every possible place it could be and assigns a probability to each one. This big cloud of possibilities, this sort of maybe I'm here, maybe I'm over there, that is the robot's belief.
Let's watch how this belief changes over time. So you turn on a robot in a room it's never seen before. Right now, it knows absolutely nothing. Zero. For all it knows, it could be anywhere, so its belief is totally flat. Every single spot in the room is equally likely.
But then, something happens. Its sensor spots a landmark, let's say a door. Now, if it's in a long, symmetrical hallway, this doesn't tell the robot exactly where it is. But it does tell it, okay, I'm almost certainly near a door. So its belief suddenly changes. It gets these two peaks of high probability. It thinks I'm probably here, or maybe I'm down there. But the robot keeps moving, keeps sensing. It sees another landmark, maybe it measures another wall. And as it gathers more and more data, those different possibilities start to collapse. The belief gets stronger, more concentrated, until finally, it's pretty darn sure, okay, I'm almost definitely right around here. This classic bell curve shape, this single peak of high probability, is what's called a Gaussian distribution. And it's pretty much the goal for any robot trying to figure out where it is.
So we get this idea of belief that's constantly changing. But how does the robot actually do that? Well, it's all powered by this really elegant, simple two-step dance. It's called the predict-correct loop.
This loop is the engine at the heart of something called a Bayes filter. And it just goes round and round. First, the robot moves. That's the predict step. And because every movement is a little uncertain, its belief gets a bit fuzzier. It spreads out. But then it takes a measurement with its sensors. That's the correct step. This new information lets it chop away the possibilities that don't make sense, and its belief gets sharper, more focused. Move and get fuzzy. Sense and get sharp. Over and over. That's the whole rhythm. Let's make this super concrete. Check out this table. Imagine the robot wants to know if a door is open or closed. At first, it has no idea. It's 50-50. Then the predict step. It pushes the door. Now, a push is more likely to actually affect an open door, right? So its belief shifts. It now thinks there's a 60% chance the door is closed. But then comes the correct step. Its sensor reads open. That's powerful evidence. It crunches the numbers, and now its belief totally flips. It's 63% sure the door is open. That's the loop in action, right there.
All right, that door example is great for getting the basic idea. But it's a simple case. It's either open or it's closed. The real world isn't so black and white. We're talking about continuous things, like position and velocity. So we need an upgrade to get from simple doors to, say, moving cars.
So how do we handle that? Well, we bring in the Kalman filter. You can think of the Bayes filter as the general theory, but the Kalman filter is its specialized, supercharged cousin. And its big trick is that it makes one huge simplifying assumption. It assumes the robot's belief is always that nice, simple Gaussian hill we saw earlier. By doing that, it can use incredibly fast math, which makes it perfect for real-time stuff, like tracking the location and speed of a car.
Of course, there's always a catch, isn't there? The standard Kalman filter has a major weakness. It assumes everything moves in straight lines. It's designed for what we call linear systems. But
The real world is full of curves. Robots turn, cars follow roads. Our world is fundamentally nonlinear.
So that leads us to the next big puzzle, right? How in the world can we use a filter that is built for straight lines to navigate a world that is anything but? And the answer is it's a beautiful math trick. It's so clever. The idea is, if you can't use one straight line for the whole curve, don't. Instead, just look at a tiny, tiny piece of the curve at a time. For just a split second, you can find the best possible straight line that approximates that little piece. You basically pretend the curve is straight just for an instant.
Now, that best straight line trick isn't magic. It has a name. It requires a specific mathematical tool called the Jacobian matrix. Don't let the name scare you. All it really is a way to find the slope of a really complex, curvy function at one single point. And by using these Jacobians to constantly make new straight-line approximations, we get an upgraded version of our filter. We call this one the Extended Kalman Filter, or EKF.
Okay, so we've built up this incredible toolkit. We have these powerful filters that can handle uncertainty, they can handle curves. What's the end game? What's the ultimate payoff for all this work? Well, it allows us to do something that honestly sounds like it's straight out of science fiction. It lets us do SLAM.
SLAM. It stands for simultaneous localization and mapping. And it is, no joke, the ultimate chicken and egg problem in robotics. Think about it. Using these filters, a robot has to build a map of a place it's never seen before, while at the exact same time, it has to figure out its own position inside the very map that it is still in the process of creating. It's locating and mapping all at once. It's just mind-bending.
And when you boil it all down, it comes back to this one really powerful idea. To know where you are, you must first build your world. A robot isn't just wandering through its environment, it's the cartographer. It is constantly estimating its own existence by drawing the boundaries of reality around itself. And that is the true soul of state estimation.